vector transforms under parallel transport, and now give you a slightly more sophisticated version of it, now that we've seen basically what's going on. Okay, so last time what we did was to draw this thing, and then we did this out, we worked it out very crudely, and in order to get it completely right, we wanted to do various fudgy things. Okay, now I'm going to do it completely correctly in a slightly more abstract manner. Okay, now that you have the main idea. So what do we want to do? We've got some loop, let's say in the 1-2 plane. In the previous class we wanted that loop to be a square. Now since we're sophisticated, it can take any shape. Okay, now we've got this loop, and let's say we've got a point here. And we want to go along this loop and see how A changes under parallel transport. That's the game. Let's keep this loop in the 1-2 plane, though even that's not necessary, but let's stick to that. Okay, now what is the basic equation that governs this? Okay, the basic equation that governs this is the equation that, so suppose A is here, it is that delta A. So suppose A at this point is some A naught of mu. I've written A naught because I want to emphasize that it's some number. It's not a function of x. It's A at that point. Okay, so now delta A, the change in A, okay, of at the point x, or along this little, well, the change in A as we go from some point here along this little thing is what? Delta A naught mu is equal to gamma mu alpha nu A of nu, and this A of nu at the point x. And del x alpha. Where del x alpha is this little vector going from x to x plus delta x. Okay, let's write this really literally. So we'll make this an infinitesimal dx alpha. This is an exact statement. This is how A changes along a little infinitesimal thing, and we want to integrate its change. But it's very important here. There are many things that are very important, as we saw in last class. We saw the main elements here. Now we're going to do it really properly. The first thing that's really important is that this is A nu of x. Okay, it's not A nu. You can't replace that A nu with 0. And the second thing that's very important is that this gamma mu is also gamma mu of x. So in order to get the change, what we have to do is to integrate this equation. Okay, now integrating this equation in general over a big path, it requires us to know a lot about, requires non-local information about the manifold, about it's not our game. We want to do it to second order in the size of the loop. Okay? And the key element of what we had in the last class that I'm going to use is this, that you remember what we did in the last class was to find how A was to first order and use that to compute the second order change. That is that in the right hand side here, you never needed an expression of A to second order. Why is that? This is because what we're doing, see, imagine that the size of the loop is some small parameter, let's say epsilon. We want to compute this object up to order epsilon square. Okay? Now to get this object to order epsilon square, we need to know this accurately to order epsilon, and this accurately to order epsilon, but we don't need to know them to order epsilon square, because whatever we have here is going to be multiplied by a small number, namely the length of the loop, which itself is order epsilon. Do you understand? So if we know what this object is to order epsilon, and this object is to order epsilon, then we can accurately compute this change to order epsilon square. Is this clear? Okay. Now, we're going to Taylor, everything is going to be expanded around this point, about the starting point. Let's say. Now that we're doing things accurately, we don't need to. There's no fudge. Okay? So we'll expand around any point, let's say the starting point. Expanding this to order epsilon, how do we do that accurately? Just by Taylor expansion. Because we're never going to go a distance more than x. And x is order epsilon. Okay? So this quantity here is gamma mu alpha nu, nu 0. I won't even write. Okay? And I'll use x. Let me call this the origin. It makes no difference. I'll choose this as the origin. Okay? Plus del theta gamma mu alpha nu x theta. Plus higher order, but we don't care. For the accuracy that we're interested in, this Taylor expansion is okay. Is this clear? Now, what about this guy? We need that also to order epsilon. Okay? But to get, what is A nu? A nu is A0 plus the change. That's how much A has changed. Okay? To order epsilon, what is delta A nu? It is given by this formula, where this is replaced by this one, and this is replaced by this one. You understand? We explained that in order to compute this change to order epsilon square, we need to keep this guy and this guy each to order epsilon. In the same way to compute the change in A at any arbitrary point. To order epsilon, we only need to keep the 0th order terms on the right hand side. Okay? So when we keep the 0th order terms, this equation is really easy to integrate. Right? It gives us that delta A nu at order epsilon is equal to gamma mu alpha nu A nu 0. All this, let me call this 0 also, just to be consistent with relations. Constant. Okay? Times x alpha. Is this clear? Okay. So to work to the order that we're interested in, we want the equation that's of interest is delta A mu is equal to, and then we just plug these two guys in this form. Okay. So this is equal to gamma 0 mu alpha nu plus del theta gamma nu mu alpha x theta into A mu 0 plus gamma nu mu alpha A0 nu x alpha. I'm sorry. Let's see. So mu, this nu is okay. Wait, what? In this term. You don't like this? I'm sorry.
Mu will be equal to
Nu. Let me just see if I got this formula right. Gamma in nu. This is the wrong formula. So this is nu, and this is beta, let's say. Thank you. So this is gamma nu alpha, and this is some beta. Thank you everyone. And I've got something else wrong.
Yes.
And then I need a dx alpha. Oh my god.
Oh yeah. So you can change that alpha to no, not to
Zeta. Okay. x
dx
alpha. Thank you. Is this right now? Something else wrong? What, say again?
No, dx alpha will be x alpha only.
No, no. Now we want to do this integration. You see, we've put what gamma is and what A is, and we're going to take those field varying values and integrate them over the loop. Do you understand? Here, what we did was, we're going to use this formula, it's an exact formula. And if for this formula, we need to keep this only to a particular accuracy, and to keep this only also to a particular accuracy. But then we have to take this and integrate it. Now, we can't just replace this by x alpha, because things here depend on x alpha. Do you understand? Integral of a constant, integral dx is x. Integral x dx is not x square. It's x squared by 2, right? Right? So it's this dangerous game to replace dx by x if things depend on x. Is this clear? Okay. Fine. Now we want to take this and integrate it over a loop. Okay, great. So now the first contribution, of course, is going to come from here. This contribution is how much when you integrate it over the loop? 0. This is what we saw in the last class. But now let's try to understand this a little better in our sophisticated sense. Okay. What have we got here? We've got a vector field that we're integrating over a loop. What famous theorem are we going to use to compute the integral over the loop? Stokes Theorem. Okay? Now Stokes Theorem is a curl of the vector field. And since this guy times this guy was a constant, its curl is 0. Because curl involves derivatives. Okay? So the only place we're going to get effects from is from the x dependence. Now anything that has two x's doesn't contribute. Because even after we take the x, the curl, there will be an x left, and x, in the end will be set to 0. Okay? Or more physically, x anyway is of order epsilon. It's one higher order. So
That's integrated over that's epsilon cube.
exactly, it's epsilon cube. So we only need to worry about this times this and this times this. So as far as we now for the thing that we have to integrate, though we actually have to integrate this, since we're doing it over closed loop, okay, we can as well replace this by, I'm putting this sign because it's not correct except for the purpose of integrating over a closed loop, gamma 0 mu alpha nu into this, gamma nu zeta beta a0 beta x zeta dx alpha, and this term plus del theta gamma mu alpha nu x theta times a0 nu times dx alpha. Okay? So, what we're going to do now is take this object and do the loop integral by using Stokes theorem. Okay? Now Stokes theorem is going to get rid of this x alpha when we take a derivative and this x alpha when we take the derivative. And just doing that will give us the formula with 2 gammas and 1 derivative of gamma. The formula that we got in the previous class. I'll leave you to fill out, just to go from there to get the exact answer. This is the curvature. Is this clear? Any questions? Anything unclear about this?
Can you repeat the last sentence?
Yeah. So now what we want to do is to take this thing and to integrate. We do that using Stokes theorem. Okay? Stokes theorem involves a derivative of this vector field. So the derivative will act on this x. Okay? It's an antisymmetric derivative. So it will take this and give you two terms with some antisymmetry. And take this and give you two terms with some antisymmetry. Okay? Multiplied by the area. Okay? You remember the curvature had two gammas antisymmetrized, product of two gammas antisymmetrized, and the derivative of gamma antisymmetrized. Okay? So now you apply this and you'll get exactly the formula we had in the last class for R. Just you have to keep track of the indices a bit carefully. Okay? This derivation is conceptually much more satisfying than the one I gave you in the last class. I gave you the previous one so that you'd see roughly what was going on. This is the more sophisticated, more correct way of thinking. Okay? What we handled only approximately in the last class was that these things were all changing as we moved. And because we had handled that approximately, we got erroneous results, which you could sort of fix up, but this is the right way to think. Okay? Is this clear? Great. By the way, it would be an interesting exercise to compute this to third order. Let's try that. Let's give you to get this thing as an exercise. Compute the circulation. You're going now over a finite loop. And to next order in the expansion in the size of the loop, compute the circulation of delta. Accurate. You see, the method we outlined here is essentially that of perturbation theory. And is essentially a method that can be carried out through to any order. So just to make sure that you understand it, carry it to one higher order.
Sir?
Yes?
So that delta mu, you have taken that it is not because of the Taylor expansion, but it is because of the difference in the vector of parallel transport.
Yeah. It's because we're talking about what we mean. You see, what are we doing? Exactly as you said. We're taking a vector and parallel transporting it along a loop. Now, when we take it, this first infinitesimal parallel transport, we know what we mean. We take the original vector and add to it gamma times delta mu. Now, for the next little segment, what do we mean? We mean we have to take the new vector A, which is A after parallel transport, and parallel transport that. Do you understand? So delta mu is the result, the change in A at any point that you get after carrying this whole procedure out.
So the A nu x in that first equation, it is
Yes. A nu x is A produced by this process.
it is not the actual vector field at that point.
No, it is, no, there is no actual vector field at that point. We're given a vector originally at one point. We've not been given a vector field. Okay? If there was a vector field, what its value at the point is has nothing to do with this area. It's a very good question. Okay? I should have made that clear. All I've given you my data to start with is A naught. I've not told you how this vector field varies in space. Okay, there's one vector. You can think of it as, I don't know, a spin sitting there. Okay? So what you've been given is the thing at one point, and then you're asked to parallel transport that thing over a loop.
But sir, in the actual, when you define that gamma thing,
Yes.
the A nu is the actual value of vector at that point.
No. A nu is what A becomes after parallel transporting A to that point.
But in covariant derivative, that A is the.
In covariant derivative, that's a different idea. See, covariant derivatives act on a vector field. in what we're doing in this exercise, we do not have a vector field. Okay? So it's a separate exercise. Forget about covariant derivatives right now. All we have is this. I've given you one vector at one point in space. I'm not giving you a vector field. Now what I want to do is to take that vector and produce a vector along a curve. By the way, not a whole vector field. Why not a whole vector field? Because it's not single valued. I'll come back to this. And all I'm asking you to do, all I want to do is produce a vector along a particular curve. This curve along which we integrate. So I've given you a vector, the data is a vector, and a curve that begins and ends at this point. And the goal is to produce a vector along this curve. How do you produce the vector along this curve? By this equation. That is, I start with my vector here, and to get the vector here, I parallel transport this vector to this point. So I get the original vector plus something small. Then to get the vector here, I take the vector that I had here and parallel transport it to this point. Do you understand? That defines the vector here, 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 here. That's what they say nu of x is. You imagine actually moving this thing by a particular rule, and this is the rule. Is this clear? Now, this is a very good question. The vector that you get this way to first order could be promoted to a whole vector field. And in fact, it's the vector field we wrote down somewhere. I've rubbed it out, but it's the delta A nu. It's just this one. To first order, it is A naught nu plus gamma nu beta alpha A naught beta x alpha. This is well defined, not necessarily for x along the curve, but everywhere. At second order, there's an obstruction to doing this. What is the obstruction? The obstruction is precisely the effect we've calculated. See, if we had a vector field, that by the time you came back, you would get 0. Because A is what it is at that point. The very fact that A, when you bring it back, is not giving you 0, is the statement that this parallel transport procedure does not produce a vector field. Do you understand? So even to know what this A nu of x is, I need to give you a curve. Let's say it in another way. Suppose I wanted to define, I've given you A naught here, and I'm not very educated in geometry. And I think what I'm going to do is to define a vector field by parallel transporting A to every point in space. These words sound good, but they mean nothing. Let's try to understand that. Suppose I did this parallel transport via this path. I will get one A. I do it via this path. I get another A. Are they the same? No, they differ by the curvature at second order. Because this is the same calculation we did. The difference between this and this is the same as closing it out. Do you understand? So the first order, this parallel transport procedure gives you a vector field precisely because everything is effectively constant as far as first order. But the moment you start seeing curvature, this parallel transport procedure does not uplift to a whole vector field. Okay? In flat space, given a vector at one point, you can easily define a vector field by parallel transporting it. What does that give you? Constant vector field. There is no, the analog of that in curved space does not make sense. Do you understand? Okay, it was an excellent question, and I should have said that more clearly. Other questions or comments? Okay, now I hope now you understand this parallel this procedure perfectly. You will complete this, and to convince me you really understand it, you will do it to third order. Okay. Okay, excellent. Now there's one more algebraic thing that we. By the way, as as we have discussed, in order to do it to third order, you will need to we will need on the right hand side here to use A at second order. This A at second order is not some field. It's only defined along the curves. You'll have to keep your wits about you. Okay? So for instance, in doing this last bit of parallel transport, you'll use A here, which is very different from A here. It's different by the curvature. Do you understand? Okay, so it's an interesting exercise. Try. Okay, excellent. Next. One more algebraic thing about the curvatures that I forgot to tell you about, but will prove very important for Einstein's equations, is the analog of the Bianchi identity. It even came up in a question somebody asked, maybe you asked. But I promised I would show you what the analog of, the Bianchi identity in gauge theory is. There's a clean analog, which I'll now explain. Okay. I want to tell you and show you an identity that the curvature tensor obeys. So let's R M I K L I K L. Okay, let's call this same. I'll write it down and then we'll discuss it. Sorry. N M N. I'm just typing. K. This was KLM. This is.
Both downstairs.
What?
M and it's been covariant. It's a covariant derivative with respect to the M index.
Yeah, covariant derivative with respect. Oh, sorry. Thank you. Let's Q. Thank you. Okay, so Mn. This is Ni KLM KLM. Yes. So just circulate. So Q K L plus R M N L Q K is equal to 0. Now the semicolon is Landau-Lifshitz notation for covariant derivative. Okay, we have usually denoted it by del Q out here. Okay, so this is the same thing as del Q R M N K L plus R M N Q K del L plus del K R M N L Q is equal to 0. Claim curvatures obey this equation as an identity. Okay. Now, I'm going to try to demonstrate the statement. Of course, it's just an algebraic exercise, but as is often the case, these algebraic exercises are simplified by working in a frame, by working in a coordinate system in which gammas vanish. Okay? So, let us first remember an expression that we had at least half derived and maybe half given you as an exercise for R NKLM. Okay, it's a pain to write down, but anyway, let's do it. plus a term which is g times gamma, gamma minus gamma, gamma. I'm not going to bother to write down all the indices in this gamma, gamma, since it won't matter to us in the particular coordinate system we use. Okay, this was the whole expression for R. Now what we want to do is to take a covariant derivative of R. What we want to do is to take a covariant derivative of R in this way and cyclically sum. Okay, that's the game we want to play. Now, this is an algebraically painful game to play because the covariant derivative, each of these has 4 gamma terms. This has 4 gamma terms and so on. But wonderful, if we work in the coordinate system in which gammas are 0, those gamma terms go away. So the covariant derivative is just ordinary derivative. Moreover, this quantity had 2 gammas. Now when we take derivative, we can take the derivative of one of the gammas, but the other one will always survive. So this is always 0. Okay? So for this exercise, all we have to do is to check that this equation is true where this covariant derivative is replaced by ordinary derivative, and we forget about this term. If that's true, since it's a tensor equation, if it's true in this coordinate system, it must be true always. Okay? So now this is a relatively simple algebraic exercise. What are we doing here? First, let's say the structure of this equation. Okay? What we're doing is keeping these indices frozen. And then we're taking a derivative and cyclically summing over the last 2 and the derivative index. Okay? So, now let's highlight what the indices that we'll choose to keep frozen are. I'll highlight them by writing them in another color. One of them was an M, one was an N. And oof. This is an M.
But that was R in KLM.
Sorry?
This was not.
Oh, thank you. let me. I'll change it. Oh God. Okay.
Keep it that way and.
Okay. And NK. Yes. I'll highlight N and K. Thank you. Can you remind me? This is M and N.
This is M and N. Yes.
And this was M and N. One of these was an N. One of these was an M, right? And this was an N and an M, presumably. Did I get this right? Somebody.
That was KM. That was KM. Yes.
This was KM here. Yes, KM and L. Is this right? Okay, excellent. Okay, so let's highlight these 2 indices, N, K. That's the same. K, M. Okay, and then what I want to do is I want to take, let's say, a qth derivative, del q of this. Okay, now this is really easy because I just take a qth derivative of every term. So all of these become d3, and there's a del xq, del xq, del xq, del xq. And then I want to check that cyclically summing over LMQ, just cyclically permuting LMQ gives me 0. Okay. So let's see. This term has an n frozen here. This term has an n frozen here. But M, Q, L, L, Q, M, the cyclic sum of these two cancel each other. Okay. Similarly, this term is a K and an N frozen here. K and an N frozen here. The cyclic sum of these two cancel each other. Is this clear? Okay. So in this coordinate system, this identity was trivial to verify. Okay. This identity is the analog in gauge theory of the Bianchi identity of gauge theory. Okay, the identity that df is equal to 0, that epsilon ijk del I fjk is equal to 0. You know that, you know what I mean, right? The completely right, completely antisymmetrizing a derivatives with f. That identity, of course, was 0 because f was dA. So if you take another derivative and completely antisymmetrize, the two derivatives should be symmetric, but then the antisymmetrization kills them. Okay, and there's a non-abelian version of that identity. Okay, this is the general relativistic version of the analog of that identity. Okay, at some point in this class, I'll have a class giving you a clear way of thinking of general relativity as a gauge theory. And then these analogs will become more than analogs. One of these identities will become the Bianchi identity of the gauge theory. But let's go a little bit, let's understand Einstein's equations and so on before we get into more formal stuff.
So if you consider the last two indices of the Riemann tensor, and it's some exact, is it some exact form?
What do you mean?
Is it an exact two form? If in the lower two indices, last two indices?
In the last two indices. Yeah, is it an exact form in the last two indices? If you keep these indices frozen, you're saying.
Yeah.
Now, is that a well-defined thing to do? You see, had these indices not been there, this would really have been a form.
Yeah.
And these derivatives would really have been ordinary derivatives. Okay? Now, because these indices are there, even though they're going along for the ride, this covariant derivative here is not just the ordinary derivative. Okay? It involves gammas because these. So it's not a completely accurate thing to say.
Okay.
It's conceptually that. Okay? It is the analog of saying that, you see, in a non-abelian gauge theory, in addition to del mu nu minus del nu nu, there's the commutator term.
Yeah.
Okay, so it's a bit more complicated than what you said. Okay. Okay, excellent. Other questions or comments?
Sir, in the tensor of R, there are 21 components initially, and the previous identity reduces one
One more. I see you've done the exercise. Yeah. Okay.
But there is another identity. Is it?
Now you see, this is a different kind of identity. All the counting that we did previously was pointwise. It was all about counting components of the Riemann tensor at any point. That identity involved no derivatives. This is a constraint on the Riemann tensor field, but it's not a pointwise constraint. You see, so it's hard to put this in that language because the number of independent components in a field is infinite. Do you understand? Okay, so it's a slightly different question. It is a constraint, but it's not a pointwise constraint.
So it's a pointwise constraint in this tensor of the higher order.
Exactly. Exactly. So if you try to count how many independent components there are in derivatives of the Riemann tensor, then this is a constraint in that. Right? And actually that can sometimes be a useful way to think. You know, the whole tensor field, because of Taylor's theorem, can be thought of as the information in the whole tensor field is information in the Riemann tensor, first derivative, second derivative, third derivative, infinite, all arbitrary number of derivatives about any one point. So one way of organizing the information in the field is by Taylor expansion around any point. And from that point of view, this constrains first derivatives. Now, because it constrains first derivatives, it also constrains second derivatives. Because we can take this and act on this with another derivative. So it constrains the tensor field in a quite complicated way, thought of from the point of view you're advocating. Okay? But it's, you know what it is.
Yeah.
Of course, in the end, the best way to think about this, in the end, the best way to think about how much information there is in R is that in the end, the information that's in R is in the information in the metric up to coordinate transformations. Because in the end, all these identities, that's what they will do. Do you understand? What you're trying to do is characterize different spaces. And different spaces are characterized by their metrics. That's the most elementary characterization. Everything else is built out of the metrics. The only problem with the metric, okay, the only problem with the metric is that, you know, there's all this coordinate transformation business. Okay, okay, let's move on. Okay, though, are you satisfied? Who you asked the question? Yes. Okay. Other questions or comments? Excellent. Excellent. So now we want to go back to the study of Einstein's equations. Okay. In order to do that, I need to introduce one more geometrical notion. I'm sorry about this, but you know, it's a package. This geometrical notion goes as follows. Consider a space-time manifold and consider a hypersurface inside the space-time manifold. So what's a hypersurface? A hypersurface is a codimension 1 manifold inside the bigger manifold. Sorry. Okay. Now, it's often possible and useful to do geometry on a hypersurface given the entire manifold. The first question you can ask is, if I know this metric of the entire space, you know, big manifold, is there a natural notion for a metric on this hypersurface? Of course there is. And let's understand this as follows. Let the coordinates in space-time be x mu.
Could we get a slightly more technical definition of a hypersurface?
Slightly more technical definition. Okay, it's the zeros of a function x mu is equal to 0. Choose a function. Okay, yeah. It's the solution of one equation in spacetime. Okay, and I will demand that this solution is, now this needs to be qualified because, you know, for instance, if there are two sets of zeros and they intersect like this, there's a point which makes it not a hypersurface. So we want smooth.
Still has to be a manifold in itself.
It's a manifold in itself. It's one-dimensional lower, and the best way to think of it is. Okay. 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 You would need here. You would need that that the zeros of this, that this equation and del f is equal to 0 are never simultaneously satisfied. That where f is equal to 0, del f is not also equal to 0. In order for this to be a good definition, that's what a mathematician would say. Okay, if that happened, then you would have these kind of singularities. Okay, but right, fine. Now, fine. Now we've got this hypersurface here, and imagine that we've got that the coordinates in space-time are x mu, and the coordinates on this, we've chosen some coordinates on this hypersurface which are y alpha. Okay, you can think of this hypersurface as the equation x mu is equal to x mu of y alpha. By the way, mu runs over 1 to d alpha is equal to 1 to d minus 1 because it's a hypersurface. Okay. Now, I want a metric on the hypersurface in the coordinates y alpha. So let me give you a formula and then we'll try to understand it. We have a metric in space-time. It's ds squared is equal to g mu nu dx nu. In this, we just substitute that x as a function of y. This becomes del x mu by del y alpha, del x nu by del y beta. This gives you a notion of distance on the manifold. So it gives you a metric. This whole thing here defines h alpha beta, the metric on the hypersurface. Now, what are we saying? You see, what we've got is a little arrow here. This is an arrow on the hypersurface, but in particular, it's also an arrow in space-time. So we want to know the length of the arrow in the hypersurface. We just compute the length in space-time. That's all we're saying here. That's what this is doing. We're computing the length in space-time just by putting in what delta x is in terms of delta y. Okay, it's a very natural notion of a metric on the hypersurface. Okay. Now, given this metric on the hypersurface, you can do geometry on the hypersurface. So you can compute, if you want, the Riemann curvature on the hypersurface, because you know the metric on the hypersurface. So you can go ahead and compute everything that you want. However, you could ask the following question. You could ask, suppose I knew all the intrinsic geometrical quantities on this hypersurface. Okay? Can I from that, is that completely in an invariant way characterizing how this hypersurface is embedded in the bigger surface? And the answer to that question is no. Because apart from the metric of the hypersurface and all the quantities you can make out of it, there is one more quantity that it's an invariant geometrical object that helps characterize how this thing is embedded inside that. Okay? In order to see that there must be one more, let's take an example. Let's say that the space that we were looking at was a two-dimensional flat plane. And let's look at two separate hypersurfaces. One example is a circle. The second example is a straight line. Now, what's the metric on the circle? But r is fixed, let's say, so it's just constant times d theta squared, just flat. What's the metric on the straight line? Constant. Clearly, this and this are different embeddings. One is a straight embedding inside the bigger space. One is a curved embedding inside the bigger space. Okay? So as intrinsic manifolds locally, these two are the same manifolds. The global structure is different. That's not the important point in what I'm trying to say. Locally, these two are intrinsically the same manifolds, but as embedding is in the higher manifold, they're totally different. That's clear intuitively. Okay? We want some invariant tensor to help us characterize this. So there must be some extra invariant information characterizing how much a submanifold bends, okay, as it's placed in its embedding inside a bigger manifold.
So the global topology of the submanifold, is it sufficient to?
Not sufficient. There's local data.
No, if we know the global topology,
yes,
and if we know that it's a circle and that's a straight line,
yes,
that still wouldn't be sufficient.
It would not. As I'm going to explain to you, there's local information. There's a local tensor that characterizes embeddings. So global topology is one number. There's in general some local information. Okay. In fact, in this case, every curve is flat. Is locally flat.
Yeah.
So this is an example of one curve. This is another curve.
Yeah.
Both of them infinite.
Yes, with the same topology.
Same topology. Clearly different embeddings. One is.
Are these curves also globally flat?
What? They're globally flat. They're certainly locally flat. By globally flat, I mean one of them is compact, the other is not. Yeah, fine. They're flat. This one is compact. This one is not. That's all I meant to say. The global structure is just about topology. Okay, fine. So we need some extra information to characterize embeddings apart from intrinsic geometry, as is clear from these examples. So there must be some tensor that we can make, okay, that comes out of the geometry of the embedding. We want everything. We want to deal with nothing that is coordinate dependent. Everything should be either coordinate invariant or transform nicely under coordinates, like a tensorially under coordinate changes. Okay, so I'm going to now define a tensor that characterizes embeddings. Physicists call this tensor the extrinsic curvature. I discovered recently that mathematicians don't call it that. I went and asked Indranil Biswas, who's a mathematician here, I had a conjecture theorem involving the extrinsic curvature. I wrote it down and I asked him, is it true? And he looked at it and said, what is an extrinsic curvature? And then he called it something else, some second fundamental form or something. So he had another name for it, but he couldn't understand me till the names were the same. So, but okay. Physicists sort of uniformly call it the extrinsic curvature. Okay, I'm going to define it. I'm going to define it. Okay, so look, given this manifold, the first thing I want to define is the unit normal vector to this manifold. I define the vector n mu. So what is n mu? N mu is a vector that is normal to every tangent vector on the manifold at that point, and has unit length measured in the metric of the full spacetime. Notice that n mu in general is not a vector on my manifold. I can't measure its length using h. I need g mu nu to measure its length. Okay?
Because it's normal?
Because, yes. In Euclidean spacetime, it's clear that because it's normal. Actually, in this course we will discuss special submanifolds, special such hypersurfaces. There's kinds of hypersurfaces called null hypersurfaces, in which the normal vector lies on the manifold. So it's possible in Riemannian geometry for a normal to lie within the manifold. Seems totally unintuitive, right? In Euclidean geometry, this never possible, as a picture is clear. How do you define the normal? The normal is defined by the statement that it's orthogonal to every vector on the manifold. Now, what is your name, please? Tunir. Tunir wanted a precise definition of the hypersurface. In terms of this f function, there's a very simple characterization of this normal. Okay? You see, for me, indices can be either up or down interchangeably. Okay? In fact, from my definition, it's more convenient to have the index down, because my definition was that it's orthogonal to every tangent vector. Orthogonality with a one form and a vector does not require the metric. Okay? So the definition is that t mu n mu is equal to 0 for all t in whatever. I won't do all this mathematics. For all t in the hypersurface. At that point.
But even this n mu, the vector still does not lie on the submanifold itself. It couldn't.
It couldn't. No. It couldn't is wrong. It cannot in Euclidean space. It can in exactly one situation. It can when n mu is a null vector. You see, because if it lay on the submanifold itself, then it would have to be normal to every vector on the submanifold, including itself. So n dot n would have to be 0. In Euclidean space, if n dot n is equal to 0, n is 0. In Minkowski space, n dot n equals 0 doesn't mean n equals 0. Light rays. Right? So one has to be careful about, and it can, and there are very special submanifolds, very interesting submanifolds in physics, namely event horizons of black holes, in which the normal vector lies inside the submanifold. We'll discuss this in great detail. Can happen. Okay? But it's rare. And for a generic such manifold, let's say space-like manifold, it will not happen.
Also, one last question.
Yes.
What does it mean to say that one vector lies along the or on the submanifold?
What does it mean to say that it lies on the submanifold? Pictorially, it means the arrow lies. Yeah? In terms of your f, what does it mean? It means precisely this. You see, it's an infinitesimal. What is a vector? It's an infinitesimal change of x's. It's an infinitesimal change of x's that continues to obey the equation. Okay, so a vector is t mu. So it's the statement that f of x mu plus t mu is equal to 0 to first order, expanded to first order in t. Okay, but what does the statement mean? It, by Taylor expansion, this is del alpha f t alpha is equal to 0. Because we knew that f of x mu was 0. And then we Taylor expand. So this is what it means to, all vectors that lie on the manifold, by definition, obey this equation.
So in the operator convention where vectors are operators on the space of functions, one could say that the tangent on the function is 0.
Where vectors are operators on the space of functions. Now this is taking us too far. This is really not how I think. Okay, for me a vector is a little arrow. Okay. And this little arrow has to obey this equation. Okay, so by the way, this tells you that this n mu here in your language has to be proportional to del mu f. Okay, now why did I go into all this? We've got this, and then its normalization is determined by the fact that n dot n must be 1. Let's say it's space. Let's say 1 or minus 1 depending on the space-like or time-like manifold. Now, why did I get into all this? I got into all this because I wanted to define a tensor that defines how the submanifold bends. I'm going to give.
How does the normalization work for null normals?
It's not normalized.
Okay.
Yeah, so there's no natural normalization then.
And one can choose
Anything you want. Anything you want. So null submanifolds are much more fluffy then, more difficult to deal with. Anyway, okay. Now, I'm going to give you a definition of an object of this extrinsic curvature. Okay. The definition is this: K mu nu is P mu alpha P nu beta into del alpha n beta plus del beta n alpha. Where P I'm assuming here that n dot n is 1. The dels are defined with respect to the upper metric, the big manifold metric. And that is necessary because n beta is not a vector field inside the submanifold. So del on n beta is not meaningful. Okay? Del acts on any vector field on the submanifold, but n beta has indices of the submanifold.
So this is the metric.
Yes, this is the metric of all of space-time. This is delta mu alpha.
Yeah, that's just delta.
Yeah. It's delta mu alpha. I wrote it this way just so that if you put both indices up, so P mu alpha would be equal to G mu alpha minus n mu n. Just to remind you that that's how it would. Okay, now what is this definition? This definition does the following things. Okay, what this is take the symmetric derivative of the normal vector. Okay, and if I just gave you this, and if you thought about it for a moment, one of you would get up and say this makes no sense. Without this is an ill-defined object. Can somebody tell me why? Excellent. N beta has indices all over space-time, but it's only defined on the submanifold. So if you try to take derivatives of it in directions away from the submanifold, that means just makes no sense. So we have to make sure that we only take derivatives on the submanifold, because that's the only thing that's sensibly defined. And for that reason, we put these projectors. The projector is to ensure that derivatives are orthogonal to the submanifold, that any of these, all these indices only point along the submanifold. Yes?
Don't we have to choose a normal direction for that?
N mu is normalized. I've chosen here n dot n is equal to 1. Okay, so I'm giving you, let's say we're in Euclidean manifold, n dot n is 1. Okay, in a Minkowskian manifold, n dot n is minus 1, we would put in a plus sign. Okay, so, right, I should put here by n square if you want. N square, I'm not doing that. Okay, okay. Now, notice by the way that because n dot n is equal to 1, if I took this index and dotted with beta, then in this term we would automatically get 0. Because this term would be del alpha of n beta times n beta, which is half of del alpha of n beta square. But n beta square is 1, so del alpha of 1 is 0. Okay? But in this term, it would not automatically be 0, because this would be the normal direction dotted with the covariant derivative of n, and that is the term that makes no sense. In order to get rid of the possibility of doing that, I've got these projectors. Now with these projectors, if I try to dot, with the normal direction, it's 0 because of the projector. So what I want to say is that in this term here, this index was automatically projected, but this index was not. Okay?
Just some confusion with the indices. So
Yes.
K mu nu that lives on extrinsic. Shouldn't it be K alpha beta then, because that's the property and K and the indices run over d minus 1, right?
Wait, at the moment in this formula here, all indices run over D.
Okay.
All indices run from 1 to D. Okay? I'm sorry if the betas may have confused you. It is theta phi I should write. These all indices run from 1 to B. Okay? However, because of these projectors here, this tensor has exactly as much information as an analogous tensor on the submanifold. Okay? By using the same kind of formula, we can define a K alpha beta equals K mu nu del x mu by del x alpha y alpha x nu by del y beta. And these two quantities have exactly as much information, because this K mu nu only had non-zero components along the directions of the manifold. If we put one index like this, that would be okay. So this quantity here is obviously symmetric. It is a symmetric tensor that in our definition was a tensor in space-time in the embedding manifold, but is often more conveniently viewed as a tensor on the manifold. In fact, it's more conveniently viewed as a tensor on the manifold because that's what it is. Because you see, here you may have thought that the indices went all over space-time, but the object is only defined on the manifold. So it's more convenient to deal with this object where the indices run only on the manifold and the object is also defined only on the manifold. So it's a tensor field, symmetric tensor field on the submanifold. Do you understand? This quantity, because it's a tensor, it was obviously a tensor, we use covariant derivatives everywhere, is an invariant characterization of something. Now, because it is derivatives of the normal, it's telling you how the normal bends as we move around. This is the quantity that would distinguish this from this in the example that we want, and is the second invariant piece of data. Apart from the metric and all its invariance, the intrinsic metric and all its invariance on the submanifold itself, that plus the extrinsic curvature and then its derivatives and so on. Okay, completely geometrically locally characterize the embedding of a submanifold inside the manifold. Okay, now of course this quantity is still not a scalar, it's a tensor, but there's a very useful scalar which is k alpha alpha, which is k traced with either g or h. It makes no difference because of these projectors. Yes? Is there a reason why we define this in a symmetric way? Yeah, yeah. The antisymmetric part is essentially trivial. Let me explain that. Apart from normalization, this thing is totally clear. See, you knew that n alpha was equal to del alpha of f. Okay? So now, this is true up to normalization. Let me hide the normalization for a minute. Now compute the antisymmetric part, derivative of del alpha. You get 0. There's a curvature term, but curvature terms acting on scalars give you 0. The curvature term doesn't matter. Okay? Now there's a normalization issue, but that's essentially a trivial point. There's no new information in the antisymmetric point. Okay? So the antisymmetric term is essentially trivial. It's the symmetric part that carries information.
Like, then there is no need to define it in a symmetric way.
You're right, there's no need to define it in a symmetric way. Okay, if you want to, we're getting more mathematics. Okay, but let's try to do this more carefully, including the normalization. Okay, so let's see. So n alpha is del alpha f by let's see, del mu del f del mu f g omega. Okay. Now, if we kept track of, now let me compute del beta n alpha. Okay. So del beta n alpha. Let me compute the antisymmetric part of that. Okay. For that, as we discussed in an earlier class, for antisymmetric derivatives of forms, and one object, one index down is a form. Ordinary derivatives, same as covariant derivatives. So it is del beta n alpha minus del alpha n beta. Okay. When the derivative acts here, you get 0. When it acts here, let's see what we get. This thing is equal to let's see, del alpha f del beta del mu f del mu f yeah, is this, what is this? Okay, we would firstly, we'd have some minus, we would have this cube, and then minus the other guy, right? Okay. So minus del beta minus del beta f del alpha del mu f del mu f by the whole thing cube. Okay. Now you see, what is this? This quantity is not 0, but what does it characterize?
Projector, if you use
Exactly. It goes away with the projector. You see, this del mu f is in the normal direction. So it's characterizing second derivatives of f, but where at least one of the derivatives is in the normal direction. Okay? So this is information, as you said, if you use a projector, it just goes away. Okay? Or if you want to think of it this way, this is information on how this f varies away from the manifold. It's not characterizing the manifold itself. Okay? Wait, but you want to know whether this thing was just automatically 0. It may be that this thing by itself is automatically 0. I can't swear to that. Okay? If it's not 0, it's something trivial. It's not got new information in it. It will be written in terms of old information. It's either 0 or something written in terms of something old. Probably 0. Probably 0. I can't think of any one derivative. Do you remember? No. I think it's probably just 0. I think you're probably right. I think you're probably right. This is redundant. Maybe I've just written it to emphasize this. That is.
In some cases, I have seen one term is there, I mean, in definition of A.
Yeah. It could well be that the antisymmetric part automatically vanishes. It feels like it should. Once you include the projector. Feels like that, right? Because if you put this and then, anyway, I can check that. I think that is probably 0, but I'm not sure. Certainly contains no new information, so if it was not 0, it would have to be written in terms of something else. There's no invariant one derivative data in Riemann curvatures, so it could only be written in terms of this thing itself.
So there is a del alpha f.
What?
There is a del alpha f externally.
You're saying that's killed by the projector.
That projector is
Excellent, excellent. So that's an argument. Right, perfect, thank you. That's a great argument. The argument is that you only got something non-zero when you acted on the normalization. That left a del alpha s, and that would be killed by the projector. Okay, so you're right. It just is automatically symmetric. There was no need to say it, but I've written it this way just to emphasize its symmetry. Okay, great, good question. Okay, great. Now, why have I got into all of this? I've got into all of this because in order to correctly write Einstein's equations, or the Einstein Lagrangian, we need these notions. Okay, so now I'm going to stop talking about these extrinsic curvatures for 10 minutes. Go back to what we were talking about at the end of the last class. Write down the Einstein Lagrangian. I'm going to try to compute its equations of motion. Okay, and then we'll see what the Lagrangian, what the action and the how we get the action and the equations of motion more precisely involving these extrinsic curvatures. Okay, so we've got this notion of the extrinsic curvature. We've defined it. You'll keep it in your mind and forget about it for now. We're switching topics for 10 minutes. So at the end of the last class, we explained that we were interested in Einstein's action, which for much of the course will be taken to be 1 over 16 pi g. Now there's some c squares, some factors of c. What? C to the 4. We'll set c to 1, okay. It's too difficult to keep track of c's. We'll restore that by dimensional analysis whenever we want. Square root minus g times r. There's the cosmological constant term as well, and we'll talk about that at some point, but that's only interesting at very long distance scales. We'll forget about it for a minute. Okay. Anyway, its formal analysis is very easy. It's very simple term. Okay. Let us take this action and run with it for a while. This is the action of just the gravitational field. So far we have not coupled any matter to the gravitational field. Okay? Just the gravitational field by itself. We want to understand what sort of dynamics this action governs. In order to do that, what we're going to try to do is to derive the Einstein field equations. Einstein field equations in vacuum at the moment. Okay? By taking this action and varying it. So what we're going to do is to take delta S, which is 1 by 16 pi g times delta of square root minus g times r, and compute it and try to write it in the form something minus square root g times a mu nu times delta gb. Okay, that's our goal. So now there are three terms in this object here. You can vary the g in the square root g. So let's write this out more carefully. So this is 1 by 16 pi g times integral minus g g alpha beta r alpha beta. Okay, two of the variations in this thing are very easy to do. So let's do those first. The first variation is really easy to do is this guy. It's just g alpha beta staring you in the face. Okay, so that gives you, so 1 by 16 pi g integral square root minus g delta g alpha beta times the first term is just multiplying this r alpha beta. Is this clear? That's where the delta hits this g upper. Next term is where the delta hits the square root minus g. Now you guys are all experts at varying determinants of matrices. Can somebody tell me what the formula for that is? What will you get from varying square root minus g? Times, now as far as this variation was concerned, this was a constant. So this was just r. Okay? You remember, right? For this I appeal to the exercise you guys solved in your first problem set. You remember how to do this. Okay? And then there is the additional term, which is plus, I'll write it as plus 1 by 16 pi g square root minus g delta g alpha beta delta of r alpha beta. These two are simple things. This thing looks pretty complicated. Okay, it looks pretty complicated, but fortunately it turns out to be a total derivative, as I will now explain. Okay. The simplest way to compute this is to use our favorite trick. That is to go to a coordinate system in which gammas vanish. Okay. Now what I'm going to do is quite subtle, so look, watch me carefully. Okay. I'm going to be in a coordinate system where gamma vanishes. But I'm going to do a variation. You see, I'm going to do a variation and not change my coordinate system when I do the variation. So if before doing the variation gamma vanished, after doing the variation gamma doesn't vanish. Okay? So though gamma in the background vanishes, delta gamma does not vanish. Is this clear? Okay? Now, there is this interesting thing. The interesting thing is that if you change metric without doing you keep sticking to the same coordinate, so that your coordinate transformations between one coordinate system and another have not changed, then while gamma is not a tensor, a small variation of gammas is a tensor. The reason for this is that a small variation of gammas is a difference between two gammas. You might remember that the gamma transformation property had the tensorial part plus an inhomogeneous term. And in computing this inhomogeneous term, in the difference it just cancels. There is another way of saying it. Right, there's another way of saying, yeah, I was going to try to give you a sort of physical argument, but let that physical argument is more confusing, I think, than the algebra. Okay? It has to do with, let it be, yes.
You see from the curvature also, since curvature is a tensor, and if you go to a plane where gamma goes to 0, then we have this del gamma terms in the
Yeah, this is change under changing a metric. Okay? So what are we doing? We've got one metric on our manifold. Now a new metric is metric plus delta G. Okay? But in describing both the first metric and the second metric, I use the same coordinates. That is, when I do a coordinate transformation, I've got x and x prime, and the same coordinate transformation map. So what I want to do is to see how under this coordinate transformation x to x prime, delta gamma transforms. Okay? I think the clearest way of saying this is if you just look at the rules, and you see that the inhomogeneous part just cancels.
Why are we even doing a coordinate transformation? We're looking for a change in the metric.
No, I'm looking for the change in the metric, but I want to understand how the answers I get will change under a coordinate transformation. I want to know whether something's a tensor or not. For that question, I need to know how it transforms under coordinate transformations. Okay? Why do I care whether it's a tensor or not? I care simply because I'm doing a calculation in my favorite frame. And then I want to be able to take that calculation and replace derivatives by covariant, the usual thing. Okay? So delta gamma under small variations, you just look at the coordinate transformation, right? Transforms like a tensor. Okay? Now this is great because what was R? R. Can somebody help me with all the indices to get all the indices?
The first and third indices get contracted.
A, B, C, D. First, help me with two things. First,
Gamma A BD, the derivative uses C.
D, C, D, plus gamma terms. This will not bother us. Okay. This will not bother us because when we take the usual story, when we take R and we take a variation, we can take the variation in one of them, but the second one will remain. Okay. Now let's see. We wanted R alpha beta, so we want this contracted.
A with C.
A with C. Okay. A. Let's see. Is there a nice? Okay.
Gamma AB that has a nice in terms of that you got it as an exercise a couple of classes.
This one.
Yeah.
Right. But I think we'll just just live with this unless. Oh, I'll just. In fact, Landau-Lifshitz presumably. Okay. Sorry. Let me just work with the simplified formula for Rik. Rik is equal to gamma n Ik del by del x n minus del by del x k gamma n m. That's this. Yes, that's this. That's this. It's just this. I think it's just contracting. Plus 2 gamma, gamma, gamma. I think it's just contracting this. Yes. Okay, excellent. Excellent. So now if I take the variation of this R, I just have to take the variations of these gammas.
There should be an I in the second term because I in the
There should be an I in the second term. Yes. Let me call this N. Oh no. Yeah, yeah. Okay. I'll just call that I. Thank you. This N here is I. Okay. Great. So now I take delta R Ik, which is equal to del by del x n gamma I n k. Delta minus del by del x k delta gamma I m m in a particular coordinate system. Okay, and then we are interested in this after we've contracted away these indices. So we have to multiply by a Gij. So we've got Gij. So this was K, sorry, K. Gik del by del xn gamma Ikn minus del by del xk. Okay. So now what? Now remember that we're in a coordinate system in which gammas are all 0. So derivatives of G are 0. Okay. So we can freely take these G's in and out of the derivative. Okay. So, claim, let me write down the claim and then we'll check it. Suppose you define the following vector, WL is equal to Gik gamma IKL minus GIL gamma IL, oh my, every time I have an I, I'll make it an N. NL gamma NKK. Okay. Claim this quantity here is simply del dot W, del dot W. Now, in order to check this claim, let's write down a formula for what del dot W is. Del dot W is 1 by square root G del M square root G.
But del W, right? The variation
del dot, oh sorry, everything is here is a delta. Sorry. Yeah, everything here is a delta. And this is just del dot w. Okay? Now, what is this quantity? This is 1 by square root g delta m square root g wm. This we had in an exercise, right? This formula. Okay? Now, this again normally is complicated because it involves derivatives of g, but in our coordinate system, derivatives of g are 0. So, this expression in our coordinate system is the much simpler expression, del m wn. So I want to check whether del L wn is what we have. I can just take all derivatives through g's. Okay? And so if I done everything right, this term should be this term and this term should be this term. Now let us check. That's correct, right? So this derivative is hitting this index. That's here, del L wn. And this derivative, k, that's also good, right? Because this index, yeah, these two are the same. See if you agree with that. Now, by the way, we've done this calculation in our coordinate system. But since delta gamma is a tensor, okay, since delta gamma is a tensor, the statement, let's write down the statement. Yeah. The statement that delta Rmn Gmn is equal to del dot w, where w is this object. Yeah, where w is this object here, is true in any coordinate system. Because the delta gammas are tensors. Okay? And this, of course, the fact that this is true has been checked more seriously by a guy called Palatini. Okay? And this identity is called the Palatini identity. Okay? So if you were not scared of algebra, you don't need to work in this particular coordinate system. You can just do the algebra. Okay? And check that this is true. It's true. Okay, we've given it an argument, but it's been more seriously checked as well. Okay. So the first thing about this, the first thing to say about this is that this guy here is a total derivative. Because it's a total derivative, it can be integrated to the boundary. Now, let me pause here to make an important point. When can you integrate total derivatives to the boundary? You can only do that when total derivatives, you know, what we've got is a fancy total derivative, a fancy covariant total derivative. But this Gauss theorem or Stokes theorem, or, you know, the theorem that says bulk integral, the boundary theorem, is basically a statement about derivatives. It's a statement that if you have del f, del by del x of f, it's f2 minus f1. Okay, it's not a statement about some fancy derivatives. It's a statement about ordinary derivatives, where derivative is a difference. Why does the fact that this quantity is a total derivative imply that it can be integrated to the boundary? Because of this formula. Because this formula tells you that this fancy derivative has 1 by square. You know, there are two things that may make you wonder, may make you think that integral square root minus g times del dot w, why should that be integrated to the boundary? Firstly, there's the square root g. Secondly, there's this fancy del. These two things cancel each other out for the case that w is a vector. Because this fancy del has 1 by square root g times ordinary derivative of something. So that something can then be total derivative. Notice that this fancy formula, that this fancy divergence had a similar formula every time W was a form. This is something you saw in your first assignment stage. So it's always true that divergences of forms can be integrated out to the boundary. However, if you had a divergence del m of Tmn, where Tmn was, let's say, a symmetric tensor, this integral square root g, this quantity is not a total, cannot be integrated to the boundary. Okay? Because if you work this out, the explicit form of this formula, there's one term that looks like this, but there is a second term. And that second term involves some gammas, it's just something. Okay? So it's very important that, you know, this idea that once you've got a total derivative of something, you can integrate it to the boundary. It's true if it's a normal derivative. If it's a covariant derivative, it doesn't always work. It works in particular when the covariant derivative is acting on forms. By the way,
just but I'm not sure whether this will be important.
Yes.
But we can integrate
Yes.
it anyway. That argument of the derivative, the ordinary derivative.
yes.
That's not a vector.
But it doesn't matter. You see, because for Stokes
Yeah,
theorem,
but it doesn't matter. So that's why
Yes.
it doesn't matter. But I mean, is it important in
Eh,
some other way?
no, it is in fact important. You know, what this thing will do will look. You know, what is the question then is, what is this going to be what boundary term will it evaluate to? So let's think. This thing will become this thing dotted with the normal vector. Okay? Now the normal vector that's the normal vector in just the sense of, you know, if the metric was 1. Because Stokes theorem is a theorem about without a metric, right?
Yeah.
Okay? If you change that to a normal vector which is really unit normalized, there would be an extra factor of g in the normal direction. That will change this square root g to the square root of the induced metric on the boundary. And so this whole thing here will become square root of induced metric on the boundary times unit normal dotted with the vector field. So even though at this level the procedure doesn't seem invariant, the question you should ask is, what is the total derivative term? What boundary term does that evaluate as something invariant? And the answer is yes. Okay? Right. Great. Excellent question. Other questions or comments?
So, you said that works only for forms that W is not a form, it's a vector.
Right. Sorry. This formula really works for, you're right, it works for I, J, K, L, all upper antisymmetric indices. The actual formula with form actually also works with lower form, but then there's extra GI. You see, what you do is you raise the thing and then do it. The right formula for forms, it works for antisymmetric objects. The right formula for forms is del by del xm square root g, g a a1, g a a2, b b1, g c, let's say it's a 3 form, c1, a a1, b1, c1. So what you're doing is you're raising this, and then, so as long as the total derivative of something, it works. But anyway, the most straightforward formula works with antisymmetric indices upper, because then you don't even need to put these square root g's. For the antisymmetric indices upper, this formula is just mu a1, these indices go along with it. The fact that this works for things with completely antisymmetric indices is something mathematicians know very well. Because for them, Stokes theorem is a theorem about forms. Upper, lower, yeah, okay. And they have this theorem which says that if you have integral of dB in the bulk is equal to integral B on the boundary. And this is what we are seeing in our poor man's way. Okay, great. But returning to more pressing issues now, this quantity was a total derivative. The fact that it's a total derivative means that it will not contribute to the part of the variation of the action from local values of g. The fact that that is a total derivative also means that in order to correctly formulate the action principle, the action principle that gives us Einstein's equations, what are you wearing? Let's say you've got space with a boundary. What are you holding fixed? What are you wearing? We have to formulate all that. We'll come to that. But let's postpone that for a moment. Okay, that's an issue about what we have to do at a boundary, what boundary conditions we have to put, what boundary curves. We'll talk about that. But let's postpone that for a moment. Okay? At least if we just look at the variations of delta G locally somewhere in the bulk of space, the coefficient of this variation is this object. And by the usual ideas of the principle of least action, if we can fix all the issues with the boundary, okay, Einstein's equation should be g r alpha beta minus g alpha beta by 2r is equal to 0. Okay. So this is the equation, the bulk equation, that follows from varying this action, not yet being careful about boundary terms. I'm going to give you an exercise which will clean up the boundary terms. Okay, and let me immediately state the exercise. That was the whole point of this whole discussion of the extrinsic curvature. Suppose now you've got a space-time with a boundary. Okay. Then if we write the action as 1 by 16 pi g square root gr plus 1 by 8 pi g square root h kappa. H is the induced metric on the boundary. See, the boundary is a codimension 1 submanifold. Kappa is the trace of the extrinsic curvature of the boundary. Show that provided you keep H on boundary fixed, you keep the induced metric on the boundary fixed, then the variation of this whole action precisely reduces to this variation here with no extra terms on the boundary. Actually, when you integrate this, you get an extra term on the boundary. That's this W, this normal derivative of W. That is cancelled by the variation of this quantity. Okay? So, this whole action, the action which is R plus K, defines a good variational principle under the boundary conditions that the metric, induced metric on the boundary is held fixed. Okay? This is Einstein's action. Though Einstein didn't understand this part. This was done much later. Okay? This is Einstein's action. And is the analog of the simple action for particle mechanics. In particle mechanics, if you take x dot squared by mx dot squared by 2 minus v of x, and you hold x fixed at the beginning and the end, then variations of all paths with these particular boundary conditions, that the extremum of the action with these boundary conditions demands that the extremum obeys the classical equation. So in the same way, so what is the problem in that situation? You've got some particle trajectories, you're extremizing the action over all trajectories that start at an initial time at one point and end at a final time at another point. Okay? the extremum of that action, that problem, obeys the classical equations of motion. In the same way, if you take the action, this action, and you extremize it over all manifolds, all metrics, that obeys some boundary conditions. What are the boundary conditions? Boundary conditions are that the induced metric at the boundary is something fixed. You see how nice the boundary condition is. It's a nice geometrical boundary condition. It's a geometrical statement about the boundary. Okay? Let's say that you want your boundary to be a sphere times time. So you specify, this is my boundary. I extremize over all metrics that at the boundary reach sphere of radius 1 times time. Extremize over all metrics that do this. Extremize this action. The extremum will obey this equation everywhere. Is this clear?
Fixing the HAB also. I mean, not only the boundary, but also the value of the metric on the boundary.
The value of the metric up to diffeomorphisms on the boundary. Okay? That's like fixing these particle. You always have to fix something. Okay? But all you have to fix here is the value of the metric on the boundary. Notice that you don't have to fix components of the metric that have one leg on the boundary and one leg in bulk. Or two legs on the boundary. You don't have to fix all components of the metric at the boundary. Just the induced metric on the boundary. This HAB, the one that we defined earlier in this lecture. Is this clear? You're going to show this in an exercise. And this is something done by York and then clarified by Gibbons-Hawking, and so is justly called the Gibbons-Hawking counterterm. It often happens the person who first does it gets ignored. Okay, excellent. So this quantity here is called the Einstein tensor. RAB minus GAB by 2 R. And Einstein's action in a vacuum gives you an equation of motion that tells you that the Einstein tensor vanishes. Now, so far we've discussed just the equations of motion of gravity in a vacuum. Okay? However, in the real world, there's lots of stuff other than gravity. There are planets, there's Maxwell's theory, there's all kinds of stuff going on. We've already discussed earlier in this course how, for instance, you would couple Maxwell action. You would put Maxwell action in an arbitrary space. Just f mu nu, square root g with. Okay? So now, suppose.
In the boundary term, what will be the sign of H there? For the induced metric?
Now that depends on the nature of the boundary. But let's suppose that your boundary, for instance, you're interested in the boundary at space. Okay? Then the boundary metric will also be time-like. So that will be minus h. Okay? But there's also the cap at plus t and minus. So should I put a mod h there? Okay. You have to suitably do it. I'm sorry, if I wrote plus h, if I wrote square root h, that was your question, right? It depends on whether the boundary is space-like or time-like. And if the boundary is time-like, it's square root minus h. Yeah, you see these corners are in real situations of so far at infinity that you don't worry. Nothing's happening then. Okay? Right, it's a good question. It's a good question. Let me, where that would happen, you see, you might worry about what happens when the thing is null. Okay? The contribution of the counter term there will just vanish. Because h will become 0. So whether it's plus h or minus h, you don't care. Okay? Right. Usually this quantity is of interest evaluated near spatial infinity. Okay? It's also of interest when we are studying Euclidean gravity. We will sometimes need to study Euclidean gravity. I will explain this. Okay, in Euclidean gravity, of course, then it's just square root h. There's no issue. Okay, fine. Let's keep going. I'm sorry I had to go a little extra. Till 1:30 is okay. Yeah. Okay. Fine. Let's keep going. So we now want to put in that we could have additional terms in the action other than square root gr. Okay. Now, so for instance, suppose our metric our action was the action we wrote down in the first class of this class. F alpha beta f theta phi g alpha theta g beta phi. Suppose we had such a term in the action. Maxwell's equations. I've written it this way, by the way, because this f is just del alpha a beta minus del beta a alpha, makes no mention of gamma, and therefore no mention of the metric when both indices are lower. So every metric dependence here is totally explicit. It's not, there's nothing hidden anywhere. Okay? Now, when we compute Einstein's equations, what will we get? Well, we'll get one additional term from varying this, another term from varying this, and another term from varying this. So we'll get some additional terms on the right-hand side of the equations of motion. But you know, this is what we'll get with this action. If we had some other action, let's say minimally coupled scalar field or some planet or something like that, you know, we'd get something else. What's the general principle? The general principle, of course, is very simple. The full action is S is equal to minus, oh, I hope I got the plus minus right here. Minus, maybe it's minus. I'll check what Landau-Lifshitz have. But he may be using a different signature convention. Let me just check anyway what he has.
And that depends on when you incorporate the matter fields, otherwise, and the extrinsic.
Well, in quantum mechanics, it depends. Kinetic terms should come positive. There's an absolute principle, you know. Yeah. You give me 1 minute. Let me just. I'll check this carefully, okay? Whether it's plus minus. I'll check it carefully with our, because Landau is using different signature convention. Maybe get a different answer. I'll check carefully with this plus or minus, one of the two. Okay, so we've got 1 by 16 pi g square root g times r plus, let's say something else. Whatever that thing is, let's call it S matter. Now, what will Einstein's equation be? We'll take this S matter, whatever we get there. So it's some S matter. So let's say that S matter, Sm is equal to integral square root g times stuff. It doesn't matter. It's something. We'll take this and vary with respect to g, because that's how we got this stress, this equation of motion. So let us define del Sm, whatever it is equal to, now there's some half and minus sign that is conventional, but let me write down something. T alpha beta, T alpha beta, G alpha beta. Now there is usually a half that I remember, but whether it's plus or minus. Minus 2. The by root g is in my square root. So minus, I hope. I'll check all the signs carefully. Okay. Whatever the variation is, it will take this form. For some object, T alpha beta. Why will it take this form? Well, sorry, this is delta G alpha beta. Well, something has to saturate these indices, and we need a square root g to get coordinate invariant. Because G alpha beta is a tensor, delta G alpha beta transforms like a tensor, this quantity here is a tensor. Okay? Definition, this quantity is called the stress tensor. of matter. Okay? So for instance, in the Maxwell field, we do this object, we do this variation. So the stress tensor of matter will be the term that you get by varying this, plus the term that you get by varying this, plus the term you get by varying this. Okay, so exercise. Compute the stress tensor for the Maxwell action. Okay, now we've just made a definition. With this definition, and once I get the signs right, okay, Einstein's equations is what? It's RAB minus half GAB R is equal to 8 pi G. 16 became 8 because of the half in this definition, and signs are up for grabs. So okay, so there's a nice right-hand side to Einstein's equations. Now the first thing I want, but the right-hand side, it sounds like a pretty formal right-hand side. Because, you know, it's almost like a fudge factor, right? I mean, whatever else you get from the variation of delta G alpha beta, we'll call the stress tensor. This is okay.
So this is a stress tensor for everything else apart from gravity.
Everything else apart from gravity. This is the matter stress tensor. Okay? This is okay. It's okay. But it would be nice if we could find some general properties of this T alpha beta. Okay? I'm now going to show you that on very general grounds, T alpha beta is a conserved, it's covariantly conserved. So this definition ensures that T alpha beta as a tensor is covariantly conserved. So let me explain that. See, Sm is some action, some square root g times some L, and we know very little about it. Okay, but one thing that we know is that it is under diffeomorphism, under coordinate changes, it's an invariant. That's what we're going to demand. Now, what does that mean? That means that if every field in the action changes by its lead under a coordinate transformation, changes by its lead derivative, changes as it does under an infinitesimal coordinate transformation. Then the whole action, actually this part, this whole thing here will transform like a total derivative. Because, yeah, the whole thing will transform like a total derivative, and the whole action here will be invariant. If you can't see that the whole thing will transform like a total derivative, forget that. It's clear that the whole thing should be invariant. Just it's coordinate invariant. Okay? Now, this action here is a function of the metric and matter fields. So, for the statement that the action is invariant to be true, the metric has to transform and the matter fields also have to transform. For instance, in the case of the Maxwell action, you'd have to transform G and A mu and therefore F. Okay?
That L over there is a stands for Lagrangian.
Lagrangian, stands for Lagrangian, something. Imagine this if you get confused about what it is. Okay? But now let us imagine that we have obeyed the equation, that we are looking at a situation where the matter equations of motion. You see, if we add this to Einstein's Lagrangian, we will have equations of motion for A mu as well as equations of motion for G mu. Let us imagine that we are on solutions to the matter equations of motion. We're not looking at this action at an off-shell point. We're looking at it where the metric equations of motion may or may not have been obeyed, but the matter equations of motion have been obeyed.
But
What?
matter equation may include the metric
itself, I mean.
No, the equations of motion that come from varying the matter fields have been obeyed. Whether that equation of motion includes the metric or not, I don't care.
Okay.
But whatever equation you get, by varying the matter fields, that has been obeyed.
Could you repeat that one?
Yes. So let's look at the case where this thing here is the Maxwell field. You have two kinds of equations of motion. You've got the equations of motion by varying the metric and the equation of motion by varying a mu. Now let me focus on configurations that already obey the a mu equations of motion, whatever they happen to be.
Can they be considered as constraints for a metric equation?
Well, you know, they will typically be no, I think they will typically be solving for a mu in the given metric. So it's not like they will constrain the metric in which this propagates. Right? In any given metric, Maxwell's equations are well defined. So what it will do is constrain the motion of a. Different ways of thinking of it. But a clean way of thinking of it is it constrains a mu given the metric. The metric will be constrained by the next equation of motion. Okay. Now, why is that important? What were the matter equations of motion? The matter equations of motion was simply the statement that the change in the action due to an arbitrary variation of the matter fields is 0. Now under infinitesimal coordinate transformation, the matter fields transform by their Lie derivatives and the metric transforms by its Lie derivative. So under an infinitesimal coordinate transformation, delta S will be equal to square root g times delta g mu g alpha beta times t alpha beta, where this delta g alpha beta now is the change in the metric under an infinitesimal coordinate transformation, the Lie derivative. But luckily, not completely lucky, there's some planning going on here. You have computed this. Okay, it's this symmetrized. Let del zeta be the infinitesimal coordinate change vector. Then there was the other thing. There was a Lie derivative of this vector zeta of the matter field phi times delta phi. Times the coefficient of the variation. You see, the general variation of the action is some coefficient times delta phi. In this case, delta phi is Lie derivative of phi. But what do we know about this coefficient? It's 0. Because the matter equations of motion are obeyed. So this is not there. So 0, the change in the action under coordinate transformation, is equal to delta S, is equal to this when the matter equations are obeyed. Okay? I've got some factors of half, minus of, but it doesn't matter because if something is 0, then minus half of it or minus twice it or whatever is 0. Okay, so we conclude that this quantity vanishes for every zeta. But t was automatically symmetric, so we don't need to symmetrize here. So we've concluded that del square root g del alpha zeta beta t alpha beta is equal to 0 for an arbitrary zeta. Let me integrate by parts. Choose a zeta field that vanishes at infinity, so I don't have to worry about a boundary term. Because zeta is totally in my hands. For every zeta, choose zeta function, that's a delta function, for instance. In anything you want, so you get square root g zeta beta del alpha t beta t alpha beta is equal to 0. This is true for every zeta field. The only way this can be true is that del alpha t alpha beta is equal to 0. This is 0 because you see, what we've done is take the variation of the action. The variation of the action is the change because the coefficient of it's something times the change in the action because the matter field has changed. But that something is the equation of motion. Okay, so that's something times the change in the matter field. The change in the matter field is the Lie derivative zeta. Doesn't matter what it is. Point is the coefficient vanishes.
Change in the matter field as in change in concentrations of matter at something like that, right?
Think of A mu if you get confused. Or F mu. It's the change in F mu because you've done a diffeomorphism. That changes just by the Lie derivative with respect to zeta.
Right, okay, right.
Okay? That's why I've written L zeta phi here for a schematic for the change in how much matter field. But none of that matters. You don't need to know the form of L zeta phi because its coefficient vanishes. Because the coefficient is the equation of motion for matter. And we're studying configurations on which the matter equations of motion are obeyed.
The coefficient is the equation of motion.
Suppose I give you an action, let's say x dot squared by mx dot squared by 2 plus minus v of x. I vary this action with respect to x. This is x double dot minus del v delta x plus boundary term. And the coefficient of that is the equation of motion. That's the principle of least action. The coefficient of the variation of the action with respect to a matter field is the equation of motion for the matter field. That's a great principle of physics, right? The equations of motion are not random, they're generated by varying an action. Okay? So this term here, it's 0 because the coefficient here, because the action is an extremum under arbitrary variations of the matter fields. So in particular under the variations that follow from an infinitesimal diffeomorphism. So all that's left is the variation because the metric is changing. That is unconstrained. We've not yet solved Einstein's equations. Okay, that is unconstrained. But the coefficient of that had a name, we gave it a definition, that was the stress tensor, and we've shown by this very general argument that the stress tensor is a covariantly conserved quantity. So, even though we don't know what this stress tensor is, whatever it is, on the right hand side will obey a covariant conservation equation. Okay, last thing I'm going to say in this lecture and then we stop, we've gone way over time. Now we go back to Einstein's equations. Now this equation looks a little better, right? Because we've got this nice equation here. We've got RAB minus GAB by 2R equal to 8 pi GAB. We know that the right hand side is not totally random. It obeys this conservation equation. And now suddenly you might get a panic attack. If you were Einstein, you might say, wait a minute, there's a consistency check. Because if I take the gradient, if I do this, sorry, G. The right hand side is 0. So it better be that the left hand side is also 0. Now that shouldn't be some new constraint because where does that come from? All the equations of motion should come from varying the action. So it should appear as an identity. Is it or is it not an identity? Is it true? Exercise. Check that this vanishing follows from the Bianchi. Einstein, when he was first writing down his equations, whenever you're doing something totally new, like this is really totally new, it's very difficult, even if you're Einstein. And you make many mistakes. Actually, in my experience, people who are too afraid of making mistakes never do anything really new. To do something new, you have to make mistakes. Okay, so Einstein got many things wrong. Before his famous paper, wrote many wrong papers. One of his early proposals was that the equation of motion was RAB is equal to TAB. He wasn't thinking from the point of view of an action, just equations of motion. He suggested this as an equation of motion with the right 8 pi g's and so on. And this was neither, it was not experimentally right or wrong. It was conceptually impossible. Because on the right hand side, we get 0 when we take a divergence. It's a stress tensor, it's conserved. On the left hand side, this quantity does not vanish. This is true, but it's not true that del A of RAB is equal to 0. Okay. I think Hilbert helped him fix this up. I'm not terribly sure of the history, but there's some story there. Okay, fine. So this is Einstein's equation. By the way, once it's come from an action, once we've got an equation coming from an action, the consistency is more or less guaranteed. Okay, so the fact that this quantity was conserved is not unrelated to the fact that this is the quantity that comes from varying a well-defined action. On the other hand, you'll never get RAB from varying an action. Okay, right. So the fact that we got it from an action more or less was basically enough to make sure that everything would work. But it's nice to see it. It's nice to see it checked. Okay, I think this completes our first order basic discussion of the formalism and the equations of Einstein's action. We've studied many interesting geometrical ideas. We've studied the notion of curvatures and intrinsic geometry. We've studied the notion of extrinsic geometry. It's extrinsic curvature. We've used the notion of Lie derivatives, the change in quantities under a vector field. And we've tried to understand the general structure of physics with diffeomorphism invariance. And we've worked out create. The right hand side is, depends on other stuff. Einstein himself was very unsatisfied with this. He considered this part beautiful and this part ugly. And much of the later part of his life, he worked to trying to geometrize everything here. Never succeeded. But there's some. This is the beautiful part. It's certainly true. And in the next class, we'll study the physics of this part of the action. One of the great things about Einstein's theory is that it gives dynamics to gravity. In Newton's law, gravity is purely a reactive thing. Gravity happens because there's other stuff. But if you ask, I don't want to put any planets. I don't want anything else. What is the dynamics of gravity by itself? That question makes no sense. Gravity by itself, in the absence of matter, is empty. It's not true in Einstein's equations. That's not true of Einstein's equations. Einstein's equations without any matter are beautiful and rich. And we'll try to understand this as we go. Okay.